All right. Hi, everybody. Can you think of a better day about glacial environments? We've got a nor'easter on the way, right? We've got a big frozen lake behind us. Just squint just hard enough.
You can imagine the glaciers.
I'm so glad you saw it first. All right. Well, thanks for joining us today. My name is Dan Harris. I'm an environmental analyst here at Quabbin DCR, Division of Water Supply Protection. One of the best parts of my job is leading our sand and gravel resources program, and where we locate, develop, and utilize some of our precious glacially derived resources. And those help maintain our internal Quabbin infrastructure. Through this and other work, I've become intimately familiar with glacial geology in Quabbin, and I want to share some of those findings with you today. Geology is such a cool discipline, right? Because it absolutely requires us to visualize and imagine as we try to reconstruct ancient environments. It can also be complex and difficult to grasp at times, so it may not click right away, and that's okay. But I suspect some of this might enter your mind maybe on one of your next outdoor adventures. That's what I'm hoping for today. So I'm going to ask you to free your imagination as we move through this landscape together. I'm going to be showing some photos of contemporary glacial environments to give you a sense of what might have been seen here in the past. We'll also get into some of the modern tools available to us that aid in these visualizations and landform identifications. We're going to do questions at the end, so make a mental or other note, and we'll talk at the conclusion. So, okay, I guess we'll get started. These are some of the landforms we'll talk about today. Outwash plains, kettle ponds, drumlins, eskers, cane terraces, pro-glacial lakes, and deltas. The information sources I'll be sharing with you today. The first are U.S. Geological Survey's official geology quadrangle maps. The second would be MassGIS's website, their Mass Mapper tool. We'll be doing some LiDAR mapping or looking at LiDAR maps. And I'll just let you know that those can be accessed via the Mass Mapper website too. So that's where a lot of this is going to come from. We have our own internal GIS, but a lot of this I'm going to show today comes from Mass Mapper. And then finally, two really excellent websites, antarcticglaciers.org and Swiss Education Glaciers Online, where most of these really excellent contemporary photos are coming from. Those are some of the online tools, but let's not forget good old-fashioned field work, right? Go out, dig a hole, see what's there, ground truth what some of the web resources are telling us. Or show up and examine one of our active sand and gravel pits, like this one, inside Gate 41 in Petersham. All right, let's talk about these USGS or official maps for a moment. As you can see, Massachusetts is divided into equal-sized quadrants or quadrangles, and each of these quads are named for a town or occasionally a geographical area or feature. It could be named for Barry or Hardwick, or we even have one named for Quabbin Reservoir or Windsor Dam. The various colors represent a type of superficial deposit, whether it's glacial till, glacial outwash, modern floodplains, swamps, you get the picture. These maps are a culmination of decades of work by geologists like Janet and Byron Stone, for example, at USGS, and many others. Us field practitioners are grateful for all the work they put in. A quick word about geologic time, because a lot of people get tripped up on this. So I just wanted to cover this quickly. Of the entirety of Earth's 4.6 billion year history, today we are discussing the Pleistocene epoch of the Cenozoic era, from 2.6 million years ago to 11,700 years ago. a blink in time, right? In terms of this whole map. It's almost nothing, right where that red arrow is. This is going to cover all of our most recent ice age. Some of you might say, what do you mean most recent ice age? There were more than one? And yes, the answer is yes. We know that in the late Pleistocene here in New England, we had at least 5 distinct periods of glaciation. And in the entire Pleistocene, perhaps as many as 20. This doesn't include earlier periods of Earth's history when ice sheets advanced, including this period under the blue oval called the Cryogenian, aptly named, when we believe almost the entire planet was covered in ice during what's called snowball Earth. The oceans were at least slush. I think that's the current research, right? But I digress. Back to the late Pleistocene, which occurred over about the last 500,000 years or so. It was characterized by a series of continental ice sheet advances and retreats known as glacial interglacial cycles. Each of these glacial interglacials lasted for roughly 100,000 years, give or take, with each successive cycle, and this is really important, effectively erasing the superficial geological evidence of the previous cycle. This all occurred until we reached what's called the last glacial maximum, the LGM, at about 26,000 years ago, lasting to about 20,000. And that's in North America. This means that the Laurentide ice sheet reached its greatest southerly extent somewhere between those two dates. That includes covering all of New England with somewhere close to a mile-thick sheet of ice. We're currently in an interglacial, as you can see on that far right side of the graph. After the last glacial maximum, the Laurentide ice sheet began to retreat back north toward Canada's polar region, where it persists to this day. By 18,000 years ago, the ice sheet was in full retreat from south to north in New England. And by 16,000 years ago, it had retreated fully north of the Quabbin. The figure on the right depicts the retreating Laurentide ice sheet's southernmost position through time with those squiggly white lines. And you can see on the right-hand side, there are some numbers in black. At the bottom, you see 18.3, 17.9, 17.0 on the way up. Sorry, that OK is covering what is the Quabbin Reservoir right here. At about 17. Voila. All right. Thank you, Nancy. So just to our west in the Connecticut River Valley, starting south in Rocky Hill, Connecticut, up to the Holyoke Range. Note the Quabbin in the upper right-hand corner, and these dates are associated with lake bottom sediments called varves from glacial Lake Hitchcock that occupy the Connecticut River Valley. This is an example of those varves. This is sort of a core sample from part of our lake bed sediments. Each one of these is a couplet, right? You see a light and a dark color, and those represent 1 year. So these really smart scientists, Ernst Antebs back in the 1920s, and then in recent times, a guy named Jack Ridge at Tufts University did this New England varve chronology. Really, really amazing, important work that gave us some of this timing we're able to see now. We have some other dating methods, by the way. So if you use carbon-14 dating on things that were once alive, and that's good to about 50,000 years old or so. And then we have something called optically stimulated luminescence dating, which essentially records the last time that particle of stone or sediment saw sunlight until it was buried. That's good for about 1 million years or so. Right. Let's use this thing. Okay. Audience question. Raise your hand if you've ever stood on or very near a glacier. All right, there's a few of us in the audience. Those of you who have may recognize some of what you're about to see. If you haven't, I'm going to show you some features that one might see in glacial environments. This photo is in the Surmullic Glacier in Nunavut in the Canadian Arctic. Now let's talk about outwash plain. Photo from Svalbard in the Arctic may represent what much of the now submerged Swift River Valley might have looked like about 17,000 years ago. These outwash plains are common in low relief areas like valley floors and are formed by glacial meltwater streams depositing sand and gravel from the margin of an active glacier. You can see that just over in the right-hand side. The meltwater in this photo has formed what's called a braided stream. And that's in your bottom right-hand corner. Beautiful example. So are there any visible outwash plains in Quabbin? This is LiDAR imagery from Mass Mapper showing elevation and shaded relief. The light yellow shows higher terrain, and the green is lower elevation. You can see on the left-hand side the surface of the Quabbin Reservoir in green, and in the bottom left-hand corner you can see that straight line. That's Goodnoe Dike right over here. This is just east of where we're standing. This is the Muddy Brook Valley in Hardwick. And this is a really great example of a reworked outwash plain. Take a little closer look sort of at the middle of that photo and look at all those curious landforms. Look at that one in the middle. Right? Look at this guy. I wonder what that could be. All these. I knew someone from Hardwick was going to be here and tell me what that was.
Slide. I tried to tell someone when they were talking about expanding the dump that I could almost see that from where I live to the east of there. They didn't believe me. I said the elevation of that is, I don't know, 500 feet above sea level. Maybe more, I don't know. Anyway.
Well, your dump is surrounded by amazing landforms. I'll say that much. All right. Here's the same area on a official geology map. This is the entire Muddy Brook Valley for the most part, give or take. You see that orange color? It's chock full of those coarse stratified water-laid deposits. Those purples are fine deposits, sort of swamps and wetlands. There may be some glacial lake sediments in there as well. I suspect that's probably the case. So speaking of lake, let's talk about proglacial lake for a moment. Proglacial meaning lakes that formed in front of the retreating glacier. These lakes were caused by the impoundment of flowing meltwater, either by glacial debris, a ridge of bedrock, or sometimes by another glacier ice. These lakes eventually drained and are no longer here in New England, but the evidence of their existence is in the sediments left behind. Here's another photo of what you might have seen here too, right? This one's in Alaska, but a very similar scene to what you may have occurred here in the Swift River Valley. So we've got proglacial lake in the foreground. We've got iceberg heading off the front and floating in that lake. Look how dirty that lake is, right? It's full of suspended sediment. And if you look around, especially on the right-hand side, there's just so much loose sediment available to be carried away and carried into the lake. So this is a source of a lot of some of the sediments we're going to see in just a moment. Get another view of a very similar situation. This time it's in Iceland. I'll point out some of these crevasses that are forming right at the terminal nose of this glacier. And in the foreground, I just want to show you this curious feature, pond in these outwash sediments. And then look at this ridge-like feature here. Pretty interesting. We'll get into that a little later too. So this is from one of our internal gravel pits. And those light gray sediments right in the middle are fine sandy layers called rhythmites laid down in a glacial lake, a proglacial lake. So you can see coarser gravelly material beneath those fine layers. It's just down here. And then on top, you can see these kind of larger rounded cobbles. You see the scale of the photo from the roots hanging down here, right? It's one big stick.
Glacial till.
This is not glacial till. This is glacial lacustrine deposit associated with a lake in the middle. And on top, we've got glaciofluvial, moved by water. Yeah. The other thing about this photo is it tells us something about the changing flow regime. Again, these are all laid down by meltwater. The fine sediments, right, almost nothing happening, very calm system. But on top, you have to have a very high energy stream to move those cobbles and small boulders. Let's talk about subglacial drainage now. And this is a very important aspect too. You can see the glacier ice in the ceiling, right, of this. And our meltwater stream flowing down the middle, and all that loose debris that's just available to be picked up by that stream if it happens to move around. So, subglacial drainage means eskers. Eskers are fascinating landforms that record the path of subglacial meltwater streams that often flow under immense pressure from the weight of the ice above. Think of these as a cast of the former subglacial tunnel that is now long gone. They're linear features, sometimes described as sinuous in form. In fact, they're always described as sinuous in form. If you see them in a textbook, it's going to say sinuous. With a typical height of 30 to 50 feet and a width at the base somewhere in the 50 or 100-foot range, although that can vary widely. Here's just a simple graphic to show you how an esker is formed. On the left-hand side, we have active ice with a subglacial tunnel, meltwater flowing through, moving sediment and debris. And once that ice has gone away, you see the cast of that tunnel on the landscape. Here's an example of one of these subglacial tunnels. This one's in Antarctica. Although the minimal thickness of the ice above and the relatively low stream flow tells us that this tunnel is in its waning stages, and the roof of that is probably going to collapse anytime now, right? But there could be an esker tucked inside there somewhere. There's another view of an esker on the landscape, outlined in yellow. In terms of composition, these are glaciofluvial deposits, again, moved by glacial meltwater. They consist of sand, gravel, rounded cobbles. They're sorted to a degree, and in fact, they're often mined as high quality sand and gravel throughout. Here's a view of what you might see in a cross section of an esker. You see those stratified layers within, and you see that ridge-like form. You get a little bit of a sense of how big that is based on the hay bales in the foreground, right? Again,
What they call bank run gravel.
this would be an example of bank run gravel. Yeah, this is one source of bank run gravel. That's right. Really good question. Are there any eskers in this Quabbin? Let's look at the superficial geology map and see. So, no, it's kind of faint, but look at this red oval I have here. This is up at Dana Common. You can reach this. That's at gate 40. If you come in through gate 41 or 42, you can reach this side of things and look at this really interesting contour line assemblage here. So we've got these long kind of linear forms. They seem to be kind of sinuous on the landscape. So these are eskers that are depicted on this map. What happens if we take a look at the LiDAR? There they are, right? Inside our red circle. Beautiful, beautiful example of eskers. And you can go in those gates and walk all around them yourself.
Is there another one above there?
Absolutely, yeah. In fact, this is a sand and gravel pit. It's almost completely dug out right out at gate 41. General public not allowed to go in there, our sand and gravel pits, but you can kind of look at it from a distance. But here you can go all day long. The next slide, we're going to look just over here, just outside the picture, and take a look at our LiDAR imagery from Mass Mapper. This is our internal GIS, by the way. Let's take a look at Mass Mapper and overhead for us, just to the west of this. Greenwich, Road, right where it crosses Pottapog Pond, that's this coming here, where it intersects with this old road called Farnsworth. Look at this beautiful cast. This is an esker. You can also see this segmented nature. They were discontinuous sometimes, right? So this section's missing, this section's missing. This section's missing because there's a road in between it. But this is a great example. I don't think anyone knew this was here until pretty recently. We were taking a look at this Farnsworth Road, and I looked at the map and said, wow, that's an esker. Let's take a look. All right, now let's talk about drumlins. Drumlins are streamlined hills, right? They're commonly elongated parallel to the former ice direction. So they have this steep kind of up ice slope and this more shallow slope down ice. Here's an example in the real world. This is oriented in the opposite direction. So up ice would be on this side and down ice would be down this gradual slope. Sometimes they occur in these field swarms. There'll be several of them all together. And you'll see why that might be in just a moment. Many Quabbin hills, several islands are likely drumlins. There are a lot of hypotheses about how these drumlins are formed, by the way. This is kind of controversial in glacial geology world. And so there are lots of these contemporary studies happening in polar regions all over the world to try and figure out this problem. So this is in Iceland. This is a glacier I would never attempt to try and pronounce. But you can see this is what's called a surging glacier coming out of this valley and surging onto the plain below. And those red features are what they believe to be forming drumlin beneath the ice. And here is an actual photo of that glacier doing that. And you can see, now that it's retreated, you see these ponds of water, and then in between are these streamlined hills. There's one there, there's another one there, they're everywhere, just like depicted in this figure. So this is at least one way drumlins are formed on the landscape.
So, what makes it different from the esker when using deposit, it's just the shape of it.
This guy's a plant, isn't he? He's queuing up the next slide every single time. So how do we know the difference? And by the way, we are going to hold questions to the end. If you don't mind, I don't mind tucking in here and there, but
Yes, someone does have a question to repeat it for the folks in the chat.
yes, good point. Yeah, I'm going to do one more slide and we'll get to your question. This is just another beautiful example of these Piedmont glaciers. See, they're exiting these narrow valleys and they're coming out onto this outwash plain. Look at that. Beautiful figures here on all sides. So how do we know the difference between a drumlin and an esker? We're almost there. Here's a LiDAR image of the Quabbin itself. Here's the reservoir just up there. Here's the Prescott Peninsula, and here are several islands. Right, we've got Curtis Island, Little Quabbin, and look at that long, streamlined nature to all of these. And you can see that on the Prescott too. Very likely drumlin. And again, one of the things I didn't mention from that previous slide is that some of them actually have a bedrock core. And this seems to serve as sort of a nucleus, a place for them to form. Here's this official map of that same area. These green shaded zones denote deep glacial till, thick glacial till. And that's what tells us that drumlins could be in that place. And so you see right on that northern edge, as that overriding glacier would have just been bulldozing debris up onto that core. You can see it here. You can see it all over the Prescott Peninsula, north side of Mount L Island, glacial till. Here we are. Here's the difference. This comes from Ireland. This is a cross section, and it illustrates the stacked nature of the glacial till within a drumlin. So if you were able to cut it in half, this is what you would see. Here is one section. Here is another stacked on that, yet another. So drumlins are made of glacial till. Eskers are made of outwash glaciofluvial materials. This was not laid by water. This was laid directly by the overriding ice. I'll also point out, this is clearly next to a body of water, right? This has got to be a lake or even the ocean. I'm not exactly sure what's happening here, but what I do know is that wave action has sorted all these materials that they're standing on, right? We've got the big stuff right next to the cliff, and as we move out toward the water's edge, we can see those smaller particle sizes. There's a sorting. And so that also tells you what it's made of. Every possible particle size from the finest clay all the way up to big boulders. No discrimination when it came to this, when the glacier was laying this down. Let's talk about cames and kettles now. Cames and kettles are a grouping of ice contact landforms, right? They're up against the active ice. They're typical of glacial outwash plain environments. Slide's really dark, my apologies for that, but here is a person, for a sense of scale, standing on what's called a cane terrace, here on this right-hand side. So when we talk about the singular term cane, K-A-M-E, it describes a mound of sediment or debris that is sloughed directly off the glacier onto the plain below. That's this situation here. We've got a crevasse. We have superglacial debris on top of the glacier that's dropped down to the surface. And once this glacial ice is gone, you see these mounds called cames. We also have cane deltas where meltwater from this glacier is emptying into a glacial lake. And then we have these kettle lakes. This is a function of stagnant ice. This glacier is retreating and breaking off pieces as it goes. And those pieces are being buried in this outwash sediment that's coming from the glacier. That burial tends to insulate those ice blocks for a while. But eventually they are going to melt. And what was once something that stood up on the landscape is now a depression that holds water. So these are kettle ponds, kettle lakes. A cane terrace, like we saw the guy standing on before, is something that's formed between the valley glacier and the valley side itself, which is probably a bedrock ridge, right? So we've got all this meltwater that's coming from the upside of the glacier, carrying debris, and stratified sediments are accumulating here. But once that glacier eventually melts, this is tucked up and up on the side of the hill and is left as a remnant. There's a lake in the valley itself. Just another quick graphic show these processes to you. So we've got this glacier that's going away. Here's the ice margin. Blocks are breaking off, buried in the outwash plain over top of the glacial till that was laid down by the direct bulldozing action of the glacier before. Once those ice blocks melt, we've got this pitted outwash and these kettle lakes. And then in a larger situation with a giant ice block, once it melts, we have a kettle lake in its place. So what would this look like in real life? Well, here's our active glacier that's backing away from here. We've got all this glaciofluvial debris in front, and we have these locations of former melted ice blocks holding water. You can also see that kind of muddy, fine nature that's helping to hold in that water too. One more graphic I thought was really cool what we might see here. So here we have our marginal stream. We have our stagnant ice backing away. Oh, look, a subglacial tunnel. And I wonder what would come of this. And we have this really cool feature called an alluvial fan that's coming off the side of the valley onto this glacial lake. See all the sediments that are being deposited from that lake. Once the glacier is gone, then this is what we're left with on the landscape, right? Our cane terrace is tucked up on the side of the hill. We've got kettle ponds in that cane terrace. We've got an esker at that subglacial tunnel location. We've got cane mounds that are all over the bottom. And our glacial lake deposit has completely collapsed, right? It's not going to hold up like these kind of firm, coarse sand and gravels. These fine layered sediments are going to be more susceptible to collapse. So here's a grainy LiDAR image. Sorry about the quality, but I just wanted to show you that this is in the Rattlesnake Hill area up in New Salem. So this is accessible from Gate 29 along Orange Millington Road, which is just sort of over here. Just make that out. And we've got a big bedrock ridge here, and up against the side of that, shown by these red arrows, is a cane terrace. It goes along this entire length. And then I wonder if anybody recognizes any of those landforms on the landscape, right? That's our cool esker. They show up. Rattlesnake Hill is just below this, just to the south, just off the photo. Yep.
So if you're in Rattlesnake Hill,
You're looking north. Yep.
north.
Yep. That's right. So yeah, again, Orange Millington Road here. And yeah. Here you go. So Rattlesnake Hill here, and we're looking up into this area. Again, it's kind of faint, but this red oval is going to point out that area that we were taking a look at. So these, again, shown by the orange, these are our coarse glaciofluvial sand and gravel cobbles that are tucked up against that hillside here. Here's our cane terrace. I'll also point out a series of kind of small circles within this. Sometimes those represent knobs. And sometimes they'll represent depressions. Now, typically on a topo map, you'll see something like this to represent a depression, right? It's got marks on the inside. Sometimes when they're this small, it's difficult to depict that on the map. But what I'll say is that several of these are pitted kettle ponds. And if you look at one up close, this is one of those ponds right on that cane terrace. This one's now a certified vernal pool. So we keep track of that here at BCR. Okay, let's talk about deltas. Deltas are really excellent, right? I really enjoy studying anytime I get a chance to see a delta, right? They're among the most complex of glacial depositional landforms in terms of stratigraphy, because of the dynamic nature of the way that deltas are formed. They're constantly changing. And so they also make up the vast majority of sand and gravel resources for mining throughout our watershed. So essentially all of our sand and gravel pits are deltas in one form or the other. It gets really complex, but today we're going to just stick with one kind of delta and go from there. To give you kind of a sense of the way that some of these can be formed, either we've got direct runoff from ice, or if the ice is completely gone away out of the picture, we still have meltwater streams bringing in sediment into this lake. So we have rain out of sediment once it makes its way in there, and eventually that's going to pile up into the bottom. Now, if you think about something called stream competence, right? That's a stream's ability to carry a certain particle size. So if it's a very slow stream, it's going to carry really tiny stuff. A raging torrent is going to be able to carry boulders all the way through. And so we can say something about the environment that a delta was built into in the stream flow regime at that time by looking at the sediments that are left behind. Another really quick, simple diagram to show us what this is about. Once these rivers make their way into the lake, they're going to start to dump that debris, right? We're going to see the energy of that stream is dissipated immediately, and all that suspended load that it was carrying is going to drop off into that lake. And so we have something called foreset beds that start to form. First, they're top sets right at the top, and then as they go down the slope, they're called foreset beds, tilted. Meanwhile, all the fine stuff is making its way out into the lake and dropping out and forming these lake deposits. Well, these deltas prograde, right? They build out into the lake over time, and eventually they're going to be on top of lake deposits. You're going to see this series of depositional forms, I should say. What do these look like in real life? On the bottom are lake bed sediments. The delta starts to build in over time, and we get those foreset beds, right? They're coming in at an angle. And then eventually that fills in, and we have active stream channel deposits right on top of that delta. So you can see this changing regime flow through time. This is recording the infilling of a glacial lake. This is at one of our sand and gravel pits in New Salem, off of Route 122 in the Gaze Hill area. I'll show you another example from one of our internal pits. And this one's really a gem. This is the one I always look forward to going to see when those guys are digging, because it changes every time, right? So, but you can see that I put these arrows here, you can see the contact between each depositional environment. So we got these like swiftly flowing gravels, and all of a sudden we get these really fine sands. So we go from active stream channel to lake bed, and on top of that, we have active stream channel once again. Go back to that, we weren't quite done. There aren't any foresets at the top of these lake sediments. Anybody have a guess as to why we might not see those? I think the clue is, again, if we're talking about stream competence, then we have these really good sized cobbles and gravels. That means that was a swift flowing stream that eventually came in here. And I think that it's eroded away off the top any of those foreset beds that might have been there at the time. Something called unconformity in geology. All right, so if we look at our superficial geology map, this is from Barry, actually, in the watershed next door in Ware River, at the Barry Heath site. This is one of our ecological restoration sites. We do controlled burns there. It happens to be a nice dry sand and gravel site, and so it's really great from an ecological perspective. It's really unique, but from a geological perspective, it's built of really impressive deltaic sequences. And we'll take a closer look at this. So here we see it mapped as these coarse glacial fluvial deposits. That's that orange color again. The yellow, by the way, is just modern floodplain. But these are glacial ice age relics. And these flat topped areas tell us something about this deltaic formation, this deltaic system. Deltas are easily eroded after the fact, and so that may be one of the reasons why we have all these intervening kind of incisions into the side of that delta. And if we look at the same area from LiDAR, you can see, again, this flat top nature of this delta. Again, this stream would come along after the fact and cut it away. So it probably extended all the way across the valley at some point. This kind of scar here is that sand and gravel pit. So that's an excavation on LiDAR, as you can see. And again, we'll go back to that same location. And this is where we are. A beautiful example, again, of a deltaic sequence changing through time. Beautiful outcrop. All right. We'd be remiss if we didn't talk about boulders and erratics, right? Everybody sees them. They really grab your attention. So I want to just say one word about boulders and erratics, and this is kind of a common source of confusion. All erratics are boulders, but not all boulders are erratics. Okay, so what I mean by that is a boulder can be anywhere and from anywhere, but a glacial erratic is an exotic boulder, transported from usually far away and sitting on bedrock of a completely different kind from what that boulder itself is. So both of these boulders, this is in the Swiss Alps. These guys are being let down from the surface of a wasting glacier. And we do see some this size around here, right? On occasion. But just to give you a sense of the environment that they were laid down in and what it used to be here. And so in terms of transport, this is a wide shot, right, of a active glacier moving, and you can see boulders just littering the surface of this thing. And these are forms called moraines. So when they're within the glacier itself, they're called medial moraines. When they're tucked in along the side of the glacier, they're called lateral moraines. And so they are one transport mechanism to move these boulders from place to place. See this big guy right on the top. And so this is in Peterson, right? Nice, beautiful, big granite boulder. And this is its contact with the bedrock below. And that's an amphibolite schist. And so that tells me this guy's an erratic, right? It's not from here. This is a tool you can use yourself. If you can tell the difference between this kind of rock and this type of bedrock, you can tell your friends that's an erratic. All right. So we've talked about individual landforms and associated sediment types. Now let's consider them as an interconnected system. So in the context of Quabbin and the Swift River Valley, we might look at the landforms extending from north in New Salem, Peter Sam, all the way south, where we are now and beyond. It's kind of a system thinking approach, and it allows us to identify various landforms and sediment types where they might be located based on existing knowledge. And so just an attempt to try and understand on a landscape scale how all of these things fit together. And so I'll return to this really cool photo from before to point out some of those same landforms that we discussed all throughout, right? So first of all, look at all of these cames, mounds, right? Directly sloughed off the ice. They're really conspicuous on the landscape. And this beautiful braided stream and this outwash channel, we've got active ice providing all this sediment and all this meltwater. Oh, look, a sinuous ridge right along the side, right? We've got eskers here, what could be collapsed lake sediment tucked in on the side of this valley. So as a system, all of these things can be occurring all at once. And just down valley here, there's very likely a glacial lake that's going to be accepting a lot of these sediments that are moved through this stream as well. All right. So with that, we'll stop. Thank you for all attending, and I'll take any questions or comments you have now.
I assume you want the LiDAR for visualizing what's underneath the trees and other parts of the landscape. Is this a good research area then? Because there's no development here.
It absolutely is. Yeah, no, thank you, Nancy. Yeah. The question is this area good for research using LiDAR as a visual aid? And the answer is, yeah, it absolutely is. We can also point out cultural resources too with the LiDAR, right? You can see stone walls all over. You can see old roads that nobody uses anymore, but they're still there on the landscape. But from a glacial geology point of view, yes, really good point, because a lot of it hasn't been destroyed. It's still on the landscape. Yeah. Anyone else? Yeah.
Global area. Today, all the pictures today are reading.
I'll say this is a little outside my area of expertise. I'm not a glaciologist. But what I will say, I think that some glaciers are probably advancing in some limited areas, but for the most part, the vast majority of glaciers are definitely waning and retreating. Yes. Yeah.
So that's funny thing. 1910 was here. And then right now, I mean, today's time, the glacier outwash was a mile below.
Yeah. Glaciers in places like Alaska are definitely retreating. We're seeing that. Yes. Yeah.
Only relevant to your presentation. Watersheds reservation is down the road here. Have you been there?
I haven't.
Oh, okay. I was going to ask.
But the glacial,
Yeah, that's been made. It was just the number of apparent erratics. I didn't know how
Yes.
until minutes ago. So,
So the question is about Rock House Reservation and the number of boulders and erratics that are at this place.
Yeah, we call it balanced rock.
yeah.
Balanced rock.
Large, ledge rock with a glacial.
At least we know it's a boulder, right? Yeah. Well, one thing we can say about an area with a high concentration of really large boulders is there's a very good chance it's glacial till, right? It came directly from the ice versus being moved by glacial meltwater. Not that it couldn't move large boulders like that, but for the most part, we're talking about directly out of that half a mile thick sheet of ice. No problem. Yeah. Sure. Yeah.
So the shoreline that gets exposed to an Quabbin Reservoir like it is now, right? You know, it has an amazing variety of rock types and shapes and sizes. Has that been theorized to all have variety of single glacial events, or do you know it's kind of origin of what is the geological history of Quabbin shoreline?
So the question is about the geological origin of some of the stones that are found along Quabbin shoreline. So, get it for you. Well, we have a couple of things happening, right? We have some in situ bedrock that's being exposed along the shoreline, right? So that's here. It may have been polished or abraded by the glaciers, but it was here, right? Long before our last ice age or the 20 before that, right? It was here 400 million years ago. But to your point, most of the loose boulders that are exposed here were carried in during the last glacial period, which would be called the Wisconsin period of the last ice age, the end of the Pleistocene. We do have some evidence of the previous age, which was called the Illinoisan, right before. So we had an interglacial in between the Wisconsin and the Illinoisan. And we do have some lower glacial tills that are still intact from that Illinoisan age. So there could be some origins of some of these stones from the Illinoisan, but the vast majority are going to be from the very last glacial advance and retreat that we had here from 120,000 to 11,700 years ago, something like that. Sure. Yeah.
So is that why we have so many boulders in New England, because of the ice shield and the glacial?
That's right. Yeah, that's exactly right. Yeah. So if you go south beyond the limit of where the ice sheets were able to make it, you know, in the eastern part of the US, you could look at like the Ohio River as sort of like the boundary. Anything south of that, really not glaciated. But up here, and you can really see it, right? You can drive along the highway and all of a sudden you're like, why are all these boulders showing up in farm fields all over the place? And that's exactly why. They were carried in by the Laurentide ice sheet. Yeah. Yeah.
Section of resources. Section of water, resources, the forest, animals, all that sort of thing. There's the landscape, the natural features that are already here for millions of years, if not thousands. Where does that fit into the management of Well, I mean, granted, they do microscope, I mean, very small excavating for, gravel, for what we use, but.
Yeah.
These areas are definitely, the landscape was protected.
Yeah. So the question is about some of these geological deposits, how that factors into some of our management decisions here at Quabbin, right? Well, you're right. I mean, like I said, on here, we do have our internal sand and gravel pits that we do utilize for maintaining our internal roads. We try to use those as carefully as possible because they are a non-renewable resource, right? Until the glaciers come back, we're not going to get those again. And we have old gravel pits that are completely dug out, right? We're all done. So we are constantly looking for new resources, which is one of the reasons I'm always looking at LiDAR. Right now, we're pretty good on that front. But in terms of, if you think about where do soils come from, right? Soils are formed into these glacial deposits, right? And so when we think about a management decision, whether maybe we're going to do a forestry cut on one's hillside, well, a soil that's really fine grained that might be formed into a glacial lake, for example, might be more vulnerable to erosion. So we have to be a lot more careful about taking equipment and machines into there versus a sand and gravel deposit that's a lot more forgiving to any, like a big machine, for example. So that sort of thing. And not to mention natural resources. I mean, I mentioned that Berry Heat site, ecological restoration that we do control burns on. Well, that's because it is a big sand and gravel glacial fluvial deposit. That's the reason why original species like scrub oak and pitch pine really want to grow in that place. It's because of the underlying resource there. So
There's area, to show the road is money brook.
There's
And they did a phenomenal restoration of that glacial.
yeah, there's a lot happening at Muddy Brook. You're right. Yeah, it's a really interesting place. Mm-hmm. Okay, sure. One more from inside. Absolutely. Please do. Yeah.
So the oil range, but they said at one time the oil range was as high as the Rockies. But, much open. So do we have evidence that these hills that we're looking at here were anything 6,000, 7,000, 8,000 foot high elevation or something?
Okay, so the question is about some of our surrounding hills and ridges and what their former height might have been, right? Their former altitude and elevation. Well beyond glacial geology. This guy's taking us back. I love it. In terms of the Holyoke Range, it's a little bit different because that's a volcanic sill that came up during the breakup of Pangaea. So we're talking, I don't know, 170 million years ago, something like that. So I don't think it ever attained heights anywhere close to the Rockies, as far as I know. I could be wrong on that, not my area of expertise per se. But what we do know is that we are part of the greater Appalachian orogeny. And so these mountains, because they're very, very old, we're almost looking at the core of what was there originally. And a lot of these were, in fact, I think, approaching Rocky Mountain heights at some point. Yeah. Thanks for the question. Okay. All right. If there's nothing else, I think we'll move to Justin and see if we have some questions from Zoom.
I believe we're all clear on Zoom at this point.
Okay. That's easy.
Great job, Dan.
All right. Thank you. Thanks everyone for coming. Appreciate it.